Do you hate math but also want to learn how to make something like this? Well then, I have terrible news for you. Jokes aside, I've also never enjoyed math that much, but I still decided to study it as part of my undergrad degree for some reason, and I'm glad I did because the applications of math are actually pretty cool, like this thing right here. This is the Mandelbrot set, and it's made entirely just with simple mathematics. Well, sorta simple mathematics. The Mandelbrot set is a fractal that is a set of complex numbers where some value c under the function z squared plus c remains bounded, with z and c both being complex numbers. This is a really simple equation that generates an infinitely complex looking result, and a quite beautiful one too. I built this actually a few years ago using CUDA and OpenGL for a GPU course I took in college. And since I started getting into shaders more recently, I thought an interesting beginner project would be to take that project and translate the code into Godot shader language. And I was right, it did end up being a pretty interesting project. In this video, you'll be able to follow along with me building our own Mandelbrot set from scratch in Godot. We'll start by first building just a static image of the Mandelbrot, then we'll use GDScript to make it more interactive so you can kind of move around it and explore it, and by the end you have a pretty sweet project you can modify, get all the different pretty colors and motions that you want, and then you can show it off to all your friends and family. Let's get started. Like I said, just open up an empty project in Godot and save it wherever you want to on your computer, and we'll start just by creating a normal 2D node, and we'll just name this one Mandelbrot. Then we're going to add a canvas layer node, canvas layer, and within that we'll create a color rect node. And on the color rect node, we'll create a new material, shader material, and then on that material we'll create a new shader, and we'll just call this, oh that was a really good name, wasn't it? No, we'll call it Mandelbrot.gd shader. And before we get started writing our beautiful Mandelbrot shader, let's go into our project settings. And we'll change the target resolution to 1920 by 1080 or whatever resolution you prefer for your monitor. Then let's close this, go back into our scene here. And for the color rect node, we're going to anchor it to take up the entire screen space. Go ahead and open up the shader file and we can expand this a bit too. We're only going to need this fragment shader, so we can go ahead and get rid of the commented out light code and get rid of the vertex as well. And while we could just write everything in the fragment function here, and honestly, I'm still new to shaders, so I'm not sure if that's really like the most optimal way that we can do it too, so we're not passing around values. But personally, I just like to break stuff into more modular functions because I find it more easier to read. So we're going to go ahead and we're going to create a function. This one will kind of be the main driver of our whole Mandelbrot math stuff here. And we're going to call it calculate Mandelbrot iterations. And what this function is going to do is it's going to run our Mandelbrot equation that we talked about in the beginning for however many iterations that we like. So from z naught equals 0 to say a value of z sub 200, something like that. Now the Mandelbrot you technically can calculate to infinity, or you can calculate it just to a certain number of iterations, and it gives you a pretty good approximation for what the actual Mandelbrot when you calculate to infinity would look like. I find that 200 iterations is a pretty good balance between looking good and also just performance, so you're not running, like 5 million iterations. So I'm going to go with 200 iterations, but you feel free to change the number of iterations that you run, and then you can see how your Mandelbrot might change in subtle ways. So to run something 200 times, let's create a for loop. So we'll say for int I equals 0, I less than 200, I plus plus, and we'll do our Mandelbrots. And I also don't really like to have just these sort of magic floating numbers hanging around. So we're going to create a variable for this, say uniform int u max iterations equals 200. And then here we'll replace that with that. And what our Mandelbrot is, it's running this z equals z squared plus c, where z will always start at 0 for our first iteration. So we can come up here and we can say vector2z equals vector2 the 0 vector. And then c is some value that we'll pick depending where we are in the screen space. We're not going to worry about what c is right now. For now, we can just say vector2 c equals vector2 0. And we'll come back to this later. And in this for loop here, we're going to want to count the number of iterations that it took before our Mandelbrot blew up. So let's create a variable to track that. We'll say int bounded iterations equals 0. And to do the actual math for the Mandelbrot iteration, again, like I said, I like to just break into modular functions. So I'll create a new function just to calculate a single iteration. And what this is going to do is it's going to return a new z vector. So we'll say vector2, and I'll say calculate Mandelbrot iteration. And this is going to take in our z and c vectors that we have defined in here. So we're going to say we'll calculate it at this z vector and at this c vector. Also, as you write the code, make sure that you're putting these functions in the same order that I'm in, just in case you aren't familiar with how like C style stuff works. It's going to need to read these functions from top down to know what to call. Okay, and instead of writing out the Mandelbrot equation, I kind of wrote in comments so that way it will be easier for us to visualize as we're programming. So we have our z equals z squared plus c, but we said that z and c are both complex numbers. If you're not familiar with complex numbers, that's okay. I'm not really going to go over like the technical mathy stuff in this video. So you can just do like a quick Wikipedia or, whatever your preferred method for looking stuff up is. This is kind of something that you go over like in an Algebra 2 class. Basically, you'll break the complex numbers into like this formula here, where z will equal z dot x plus an imaginary number times z dot y. And we say that z dot x is the real component of z, and z dot y is the imaginary component of z. And since it's squared, we square it. And then for c, it's the exact same thing. We have c dot x plus I times c dot y. Then we can expand this out further by doing all of the multiplication stuff, and we'll get this formula here. And this is kind of what we'll use in our program to do the actual calculation. But I'd say it's good, like if you're writing kind of more complicated mathy stuff, or just anything that might be kind of harder to understand when you're writing your code, just make sure that you kind of give comments so that way your future self or somebody else will be able to understand the code that you wrote a long time back. Because when I was going through my OpenGL and CUDA interop implementation for the Mandelbrots, I was very happy that I had the comments that I did. Otherwise, it would have taken me longer to make this video. Okay, enough being said, let's calculate this Mandelbrot. So first, we'll calculate the new real part of z, which will be the x component. And let's store it in just a temporary variable for now, because we're going to also need to use the x component in the imaginary calculation too. So say x new equals z dot x times z dot x minus z dot y times z dot y plus c dot x. So we took the real components, zx squared, zy squared, right? So the real component here would just be anything that doesn't have the I attached to it. And then we add cx. Then we'll calculate the new y value. So z dot y equals 2.0 times z dot y times z dot x plus c dot y. And now that we've used our x value, we can go ahead and store z dot x equals x new. And then we can return our new iteration value. Cool. So now in here, we can do z equals calculate Mandelbrot iteration, and we'll pass in our current z vector and our current c vector. And then after calculating the Mandelbrot iteration, we'll want to check to see if z is still bounded or not. So again, create a new function. We'll say bool is Mandelbrot iteration bounded, and it'll pass in our z vector. And we say that our Mandelbrot iteration is still bounded if the magnitude of the z vector is less than 2. And again, there's mathy stuff reasons for that being the case, which again, I encourage you to look up if you're a little more interested. But we can also save ourselves a computation by just saying if the magnitude squared is less than 4. That way we don't need to perform a square root operation. So to get the magnitude squared, we would just say return the dot product of the z vector with itself, and if that is less than 4. Cool. Then now back in our main driver code, we'll check if is Mandelbrot iteration bounded, our new z vector. And if it is, we'll say bounded iterations plus plus. Otherwise, if it's no longer bounded, then we know that it would never be bounded, right? Because it's just going to keep growing larger and larger. So once it's past 4, it's never going to go below 4 again. So we can just stop doing our Mandelbrot calculations here, and we can say break. Then at the end of all this, actually, I had this wrong. This should not be a void function. It should be an int. And at the end of this, we'll return the number of bounded iterations. Okay, perfect. So that's pretty much, actually, that is exactly all that we need to do our math for our Mandelbrot calculations. So now let's try to use this bounded iterations value here to color our Mandelbrot. And for now in our fragment shader, we'll just say that any value that was bounded, we'll color it black. And any value that is not bounded, we will color it white. This will allow us to visualize our little mathematics that we've done. So in here, let's store the bounded iterations. So we'll say int iterations equals calculate Mandelbrot iterations. And we'll say if iterations equals u max iterations, we will color this black. So say color equals the black color, which will just be all zeros, then make sure it's visible. And then we'll say otherwise, we will color this white. It should be all ones. Very exciting. And if we move this down, we'll see right now that it's all black. And that's because we just hard-coded C to be 0 for now. So it's going to return the same value at every single point on our shader. What we want to do is we want our Mandelbrot, this value of C, to be mapped to whatever pixel value it is on the screen. And to do that, we can use our UV coordinates, which we can access from the fragment shader, but we can't access it from the calculate Mandelbrot iterations function on its own. So we're going to take that in. So we're going to say vec2 UV. And then in the fragment shader, we'll pass in the UV. And we're going to map our UVs to the complex plane here by doing this little equation. We're just going to say C equals UV minus 0.5. What this is doing is instead of making the center of our image where the UV is 0.5, 0.5, it's going to make it 0, 0, which will make it easier to chart our Mandelbrot, since that's how we would normally graph it, right? We would have 0, 0 in the middle here, not 0.5, 0.5, it'd be kind of weird. But we can already see here that our Mandelbrot is starting to show up a little bit. But we can't really see the Mandelbrot yet in all of its glory. To do that, we're going to need to zoom out a little bit. We can do that by coming to here and multiplying it by a certain scale factor. I think 2.5 looks pretty good. And we can see it is starting to look a lot more like our Mandelbrot. But it still is off-centered a bit. We have a lot of white space over here, and there's a lot of Mandelbrot that's just kind of hanging off to the side. So we can kind of shift where our view is a little bit more by adding a vector to this equation. I think a offset that looks pretty good is negative 0.50. And we'll just add that here. And boom, there we have it. That looks like a pretty nice Mandelbrot. But to fix my OCD, let's go ahead into here and let's move these little values into their own constants at the top. Say uniform vec2 u center. Also, I don't know if this u prefix is really actually how you're supposed to name these variables, but at least I found like when writing my C++ code, naming member variables with an m underscore was really helpful for figuring out which ones were like member variables. So I'm just kind of using that same pattern here. You don't need to follow it. I don't know if it's actually technically correct or not, but it helps me visualize my code better. Anyways, u center equals, say, negative 0.50 by default. And then make sure that we say vec2, can't just infer it. And we'll say u center, and then uniform float u scale equals 2.5. And then we'll say u scale. And now when we just run the scene, we can just do select currents, fine. We'll see our Mandelbrot, which is awesome. But we can't really do anything with the Mandelbrot. It just kind of sits there. We can look at it, say it's pretty, but what if I like wanted to go see like this part of the Mandelbrot down there? Because the cool thing about these fractals, Mandelbrot and a bunch of other stuff that I haven't really explored too much yet, but I'm going to, 'cause these fractals are really cool, is they'll just repeat forever. So you can like zoom in and there'll be these different patterns that emerge as you zoom in more and more. And some of them will be repeating, some will be different. And that's where like this Mandelbrot truly shines, is when you get to like zoom in, move around it, and then give it like different color patterns and different animations and stuff. So anyways, we're going to go ahead, make a GD script file, and we're going to use that so that way we can go and explore this Mandelbrot. So Mr. Black and White Static Mandelbrot, we love you, but let's go ahead and make you a little more interesting. And don't worry, he can't hear us, so he won't feel too bad. So let's go ahead to the root node here, create our script. Mandelbrot.gd is perfect, so we'll load that. And let's go ahead and get to work on making it interactive, which is actually a lot simpler than you would think. It's just setting some shader properties that we already exposed in our shader script. Specifically updating this center value and this scale value. And that's all we need to do. Also, what we're going to need to do is define some inputs. So again, go up into our project settings. Let's go over to input map. And let's define some actions. Let's create one for moving up the Mandelbrot, and I will map it just to the W key. Then let's create one for going down the Mandelbrot and map it to S, or just map it to whatever values prefer. Doesn't really matter. It's called right, left, and then zoom in, which I'll just map to being a mouse button press, left mouse button, and then zoom out, which will be the right mouse button. Cool. And to update these variables that we have exposed here in the shader, we're going to need access to that shader material. So let's click on our color rect here. We'll just access it as a unique name in our script. And let's click and drag, holding down command, and it will create an onReady variable here for us. From the color rect node, I want to get the material property. So we'll say dot material, and let's just go ahead and cast it as a shader material. And then we can just let it infer the type. That way this error can go away here. And in our GD script, we're just going to want to keep track of the center and the scale on our own. So we'll create var m Mandelbrot center. And again, this is just kind of what I've picked up from doing C++. I know it's technically not like GD script proper stuff to prefix with an M, but again, it just helps me read my own code easier. So maybe you can try it out. If you don't like it, not a big deal. Please do not crucify me in the comments for not being exact proper with my GD script. So anyways, we'll set it to a vector 2, and this will be negative 0.50. And then we'll also create one for the scale, and this will just be 2.5. And then also we're going to want to zoom in at a certain speed and move around a certain speed. So we'll just define some constants for that. Activity. And I found, this is just what I found playing around with. I found like 0.25 was good, and actually the same was good for the mouse sensitivity too. So we can just copy this and we'll say mouse sensitivity, and perfect. Now let's go into the ready function, which we're going to want to have. And in the ready function, we are going to, actually we'll just say pass for now, because we're going to set some properties that we'll define later. And in the ready function, we're going to want to set our Mandelbrot shader's properties to just be whatever we've set here. That way we can just override whatever in our shader. So to do that, we'll get the Mandelbrot material. Actually, I want to rename this too from color rect to the Mandelbrot material, which is a better name for it. So we'll say Mandelbrot material dot set shader parameter. And the shader parameter is just going to be these parameters that we defined here already, these uniform variables. So we just get the variable name. So we'll say the center, we'll set it to our custom Mandelbrot center. And then we can just copy this. And for the scale, say u scale will be m Mandelbrot scale. And we can already see that this will overwrite what we have in our shader script here. If I just change this to something like 1.5, go into 2D, and this is going to be reflecting what we have in our shader file here. But if I run it, we'll see that the scale is different because our GD script code is overwriting what we've set. Cool. Now let's make it so during the process function, we can move around this thing. So let's create the process function, or I guess use the process function might be more accurate. And we're going to get our move direction first. So we can say move direction. And we can get the normalized input vector with our up, down, left, right by using get vector. And we can say left, right, up, and down. Then we can also get our zoom direction by saying zoom direction. And that will be input.getAxis, and that will be zoom in and zoom out. Then we only need to update our shader properties if there actually is like a change in the direction of our move and our zoom. So if either of these evaluate to like the 0 vector or 0, we don't need to do anything. So we can add like a little check for that. So we can say if move direction is not equal to the 0 vector, so vector 2.0, then we'll update our Mandelbrot center. And how we'll do that, it will just say Mandelbrot center plus equals, and it'll be plus the move direction times our move sensitivity. I just realized that I named this mount sensitivity. This should be move sensitivity. And we also want to take into account what scale that we're moving at too, because we're going to want to move by less when we are looking at things at a smaller scale, right? That way we're not moving by the same amount, say, as if we were zoomed out, because then we would move really fast and it'd probably give you a massive headache and you wouldn't be able to see what you want to look at, and it'd be very frustrating and annoying. So let's multiply this by our current Mandelbrot scale. And to make sure we're consistent at different frame rates, of course, times delta. Then we're also going to want to do the set shader parameter thing. And actually here as well, we'll just make another function for it. So we'll say set Mandelbrot center. This will be a void function. And we can just copy this here, paste it in. And actually, let's create another one while we're at it for the scale. So we'll say set Mandelbrot scale. This will be scale. And then the Mandelbrot scale. And we can replace this, this. And we can set it in here. And then let's replace this with this. And then in here for our zoom, we can say if our zoom direction is not equal to 0, that means that we have some change in our zoom direction. So we will calculate the scale actually the exact same way. So come in here, except this will be the zoom direction. This is the Mandelbrot scale. And then we'll do it by zoom sensitivity, Mandelbrot scale times delta. Then make sure that we call set Mandelbrot scale. And that's all there is to our GD script. It's actually honestly pretty amazing like how simple you can have of a GD script file and then also a shader file, and how interesting and cool the results can be on the screen. You look at this and you think, oh my gosh, like how is this even possible? But then when you sit down and actually work through it, it becomes a lot simpler. That said, if some of this stuff is confusing to you, doesn't make sense, don't let me saying, oh, like this is like simple. I've also like I studied, math in college and everything. So don't let that scare you away. Like if some things don't make as much sense, like that is totally fine and totally normal. Like don't panic. I more just kind of mean with like the amount of lines of code written, it's amazing what kind of results that you can get. Okay, but now let's see this in action. Let's go into our 2D view. Let's run it. And I just realized that I want to change this back to what it was before. Let's do 2.5. Okay, now let's run it. And if we move around using the WASD keys, we can move around. And the really cool part is when we start to click, we can start to zoom in on different parts of the Mandelbrot, which is really, really, really cool. And we can see here, we already have like these little like swirly things going on. Like those things are cool, right? It's like little like whirlpools as we get closer. and it just goes down like infinitely, right? It just goes down forever, which is like sick. So this is already just really pretty to look at, and there's so much that you can do. Let's think about like the kind of things that you can do with this stuff to visualize, your own Mandelbrot. The different like color palettes, color schemes you can give it. Because right now we're just coloring it black and white, depending on if it is bounded or not. And remember, we said that anything that we colored black was bounded. So all these values are technically, or not technically, they are within the Mandelbrot set. And like I said, it makes a nice little butt. Okay, cool. So now that we can move around the Mandelbrot and we can visualize stuff and we know what we can do with it, let's make this even more interesting to look at now by giving it a bunch of pretty colors. Let's open up our shader code one more time. And again, let's create another new function, and we're going to call it color Mandelbrot, which is just going to return a color. So we're going to say color Mandelbrot, and we're going to have it take in the number of iterations that the value of C took to become unbounded. Or if it stayed bounded, that's cool too. And to stop our little ID from freaking out here, let's just create a color variable called color, and let's just set it to black by default, since that's kind of what we're using to visualize stuff that's within the Mandelbrot set. And then we'll just have it return a vector 4 of the color and make sure that it's visible. Cool, and there we go. Then in our fragments, we're still going to keep the number of iterations that we took here, but in here, we're going to set the color equal to our color Mandelbrot function, and we'll just pass in the iterations. And right now it's black, so just to keep it looking how it was before, we will say if the number of iterations equals the max iterations, then color equals the white color. Well, actually, this is reverse of what we had, but anyways, you get the point. Actually, if we just want to reverse it back, we'll just say not equal. And then there you go. Cool. And an interesting way to color our Mandelbrot and how we can visualize it even more is by assigning different colors based on the number of iterations that it took before it became unbounded. And what we'll end up finding is that these values here on the edge, probably what we would expect, right? These will be different color values than ones that we find further out here, right? Because we're getting further and further away from where our bounded values are. Naturally, kind of makes sense that they would be the same color, whereas ones over here, you'll get more color variation, which, ends up being really, really cool. So let's start off here in our color Mandelbrot function, and let's go ahead and let's normalize the number of iterations, because right now this can be from 1 to 200. So with shaders, we typically work with values from 0 to 1, so I'm going to do that right now. I'm just going to do floats, norm, iterations. And to do that, we're just going to take the actual number of iterations that we have, and we're going to divide it by the maximum number of iterations. And this will give us a value of 1 if number of iterations equals max iterations. Otherwise, it will give us some decimal value between 0 and 1. And to do a simple visualization with this, we'll come into here and we can say if the norm iterations is less than 0.33. So if we got a third of the way there, all black now, we can just color the red component. So we'll just say color red is 1, and boom, we can already see it, right? So this is going to be our part in the Mandelbrot where it took the least amount of iterations before it, quote unquote, blew up. Otherwise, if it got a little bit closer, I can say number of iterations is less than 0.66. Then we'll color the blue components. And see here, we can see that it's more kind of like on the edge, right? Which is pretty cool. And then otherwise, if it got most of the way there, but didn't quite get the way there, so it got over 2/3 of the way there, but not the whole way, we'll color the blue components 1.0, and this is my mistake. Again, we should color the green component here. Boom, there we go. So as I talked about before coloring all these, it makes sense that we would have red here on the outskirts, and then we get green, and then we get to a layer of blue. And this looks pretty cool already. But these colors, again, like it's static, right? If we're gonna move around here, they're always gonna be consistent. And honestly, just having it all the way red, all the way green, all the way blue is a little tough on the eyes to visualize and still not quite that interesting. I like to look at stuff when they're animated because it's really pretty and my eyes get really big and I'm like, wow, this is gorgeous. Can't believe that I wrote this with my shader code. I don't need to learn pixel art anyways. Just kidding. Probably should learn pixel arts, but that's for another time. So to come in and do our little animations, I did a lot of experimentation and I found actually this really simple formula that gave me the best results that I enjoyed the most personally. But obviously this is your Mandelbrot, so feel free to kind of play around with stuff and make it your own. I'll just assign it to a value here I'll call color change since it's going to be the exact same for all of them. And I found by taking the absolute value of the sine of time since our shader began times the normalized iteration counts times some constant speed, which I found that 3.0 was the best. And again, actually, let's go ahead, let's copy this value here. Define another variable uniform float u color oscillation speed equals 3.0. Copy that, paste it in, and then let's replace our 1.0s. Oh, see, it's already getting pretty cool. Yeah, look at that. See, look at this. It's like these like pillar things that are happening. I mean, isn't this like sick? Like look at these pillars and you get like these cool like patterns that come down as you go further and further, and it's like it looks like it's like breathing, and you have like this cascading like effect of the darkness going down, and it's like shimmering and changing. It's really, really cool. So basically what this is doing is we are taking the sine of time, right? So this is going to go between -1 and 1, but then we take the absolute value, so it goes between 0 and 1. That way it doesn't stay dark for too long. And then we're going to have everything move at different speeds based on the number of iterations that it took, right? So that's why you kind of see like this sort of cascading effect, right? Like if we didn't have the iteration count, then everything would go at the exact same speed, right? Which just is kind of like flashy, and it doesn't really look like quite as good, right? But if we have it move based on like the number of iterations, then we have stuff that's reaching a value of 0 and a value of 1 at different times. And since they're so close together, it's going to look like it's just moving up and like moving down. And yeah, I mean, I don't know. I think this is really cool. And it's kind of incredible how just such a simple formula can give you this. And then this like oscillation speed, this is just basically like the rate that we're moving at, right? So like if I had like 5,000 or something, right, then, it's a big spaz party. And if you like this, more power to you. Go for it. But I do not want to suffer an attack. So we're just going to change it back to the normal speed that we had before. Now we can go ahead and we can run this, and look, like it starts out like everything's like super dark and it gets like boom, gets all like glowing, expansive, and then you come in, you can zoom around, and I mean go nuts. Like a lot of these different parts like of the Mandelbrot will show you different things, right? Like there's different patterns that emerge at different times. Like we have like this little area out here, which is just like super cool. I think like personally my favorite part that I like to look at is down like this thing like here. Like I think like these things are like really neat to look at, and I love how defined these pillars get like so quickly by doing this like very simple like formula calculation. But yeah, it's really, really cool to see how this looks. And now here, like down here, you have like a little like peacock guy going on here, right? You got like the blue, and then one thing that I will say is as you zoom in more and more, eventually it will become pretty pixelated. That just has to do with floating point precision. The math is all still correct. But I didn't mess around too long to see like if there's a way I could really work around that. But maybe, like I said, like if you want to, then feel free, go nuts, because this will keep going. But yeah, you see it starts to get like a little pixelated. Maybe it can be your Minecraft Mandelbrot. I mean, who knows, right? And one other thing that is really cool about this formula too, it takes a little bit of time, but eventually at some point, let's see, I'll open up this shader. This value here will evaluate to 0 for literally every single point on the screen. And when when that happens, it's like the whole entire thing just goes super dark, and then it'll just like pop out like a light. It's like somebody turns the lights off and then turns them immediately back on again, but then the light just like spreads like throughout the whole room, right from like a middle point, and it's gorgeous. I think what I'll do is I'll just go ahead, I'll skip ahead and I'll show when that will happen. If I have anything interesting to say between now and then, I'll include it in the video, but it's just gonna be me blabbering on about Mandelbrot and colors and math and crap. And I don't think anybody wants to listen to that for another 5 minutes or whatever it is. Let's just go and pick out a really cool spot to look at. Maybe like whatever cube. So yeah, you can see it starting to like kind of cascade down and get like really thick. It's almost like a gooey goop, if that's the word for it, right? And then like a boom, 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 and then it's gonna get dark. So it's getting darker and darker and darker, and then it's gonna converge, and then it's going to pop. And that I love looking at that, and then how it spreads out too. Oh man, I feel like I shouldn't even be talking over it, right? I mean, you should just be enjoying this, not to listen to my voice. But yeah, it's so cool. And then it'll just keep repeating on. And yeah, it's sick. So anyways, that's it for today's video. Please, I encourage you to play around with this Mandelbrot more. Come into this little color equation here. Map different values, play with different functions, go nuts, go crazy. This is your Mandelbrot. Show it to your friends, show it to your families, and they'll be like, wow, that's a really cool Mandelbrot. And you'll be like, yeah, it is. Another thing you can do too is you can play around with different max iteration count. And this will vary your Mandelbrot slightly, especially more at the edge, because if you, for example, like increase or decrease the number of iterations that you do, you'll get more accurate or less accurate approximations. Like, let's just kind of look at 50 here. Yeah, see, I mean, like it looks pretty similar, but I'm sure if you zoomed in, it looked a little different. And then what happened if I just did like 5? Hold on. Oh, well. Oh, wait. Oh, wait, that's why it looks so similar. Let's go to 5. Yeah, see, now you have like a Atari Mandelbrot or whatever, right? I mean, that's kind of cool too. So let me know if you want to see more videos on different types of fractals, or if you want me to do some more other interesting stuff with shaders, and I'd be happy to do it because I've been having a really fun time working with this shader stuff. I'll leave a link to the final fully documented project here in the description. I'll just kind of go through, add some comments here, add some comments in my GD script code, maybe do like a little readme action, who knows? But yeah, that's it. So thank you guys all so much for watching. Please take care of yourself, and I'll see you in the next one.